Okay, so in computer science syllabus, we have three types of number systems. There is denary, there is binary, and then there is hexadecimal. In denary number system, that's of course the regular number system that we use. And in denary numbers, if you notice, the total variety of unique digits that you have starts from 0, and it goes all the way till, so it has 0 1 0 1 2 3, so on and so forth, all the way till 9. Okay, after 9, the numbers that you get, 10 11 12, all those are actually just combinations of these 10 digits that we have, right, from 0 till 9. uh, After binary number system, we have the binary number system, and in binary numbers we just have two unique digits. We either can have 0 or we can have 1. Okay, all right. Then there is a third number system, that is the hexadecimal number system. In hexadecimal number system, let's look at what variety of digits we have over here. Okay, so in hexadecimal number system, it starts off with 0 1 2 3 4 5. So it's just like a regular denary system, if you notice. But after 9, we get A. So we start to have letters instead of numbers over here. And again, notice that what we are really creating over here are unique digits for a number system. Like just the way in denary, we go from 0 till 9, but after 9 we start to have combinations of digits from 0 till 9, right? In binary we have just 0 and 1, but then we can also have combinations of zeros and 1 and 1s, as we saw in the last couple of videos. But in hexadecimal, we go all the way till 9, and then after 9, in order to have more unique single digits, we have A, we have B, we have C, we have D, we have E, and we have F. Okay, now what value, I mean, at the end of the day we are just creating a number system, right? So what values do these letters A, B, C, D, E, F has? Okay, so I mean, to no one's surprise, this A actually is an equivalent for 10, B is an equivalent for 11, C is an equivalent of 12, D is for 13, E is for 14, and F is for 15. All right. So the letters, the English letters that we start to have once we cross once we the English letters that we start to get after 9 are basically just a different way of representing the same denary values all the way till 15. Okay, now one can ask that why do we not have values after 15? I mean, that's just a convention that we follow. Okay, so I mean, for the rest of the values, whatever the values themselves are, they are the what represents their denary equivalent as well. Okay, so one thing that you should again remember is that all these hexadecimal numbers that we have over here can have their binary equivalent, and their binary equivalent would be found in just the same way as we found found the denary equivalent of 213 or 170 in the previous videos. But for over here, if you look at, we don't really have really large values, right? Because we don't really have really large values, we don't need that many bits, that many powers of 2, like the way we need it over here, right? We had to go all the way till 128 because the numbers we were getting were actually quite large. Over here, the largest number that we have over here is F, which is a representation for 15. So we only require 4 bits, not 8 bits over here. And what are those 4 bits? Those 4 bits would be the those 4 bits would be the representation. Wait a second. Okay, so those 4 bits would be the powers of 2, starting from 1 all the way till 8. Okay, so for 0, of course, the combination would be 0 0 0 0. So I'll just copy that over here, right? So 0 0 0 0. For 1, we will just have to make this one as 1, right? And I'll just speed up the process now. So for this one would be this. You can check this against the registers, because this gives you 2, right? So just the same way, I'll just go ahead and write down the rest of the conversions. You can pause the video to check them yourselves. For 7 it will be 1. Now for 10 it would be 8 and 2, right? Again, you come over here, A is represented by 10, and for 10, in order to be able to represent 10 using the 4 bits, we will have to make 8 as 1 and 2 as 1, and the rest of them would be zeros, right? Same way, in order to represent B, we have to make up a total of 11, so we will make the 1 as 1 also. Okay, so 1 0 1 1. Then for C, we will have 12, so these two. For D, it will be 13. For E, it would be 14. And for F, it would be 15, which is all ones. That's why we used exactly 4 bits, because the maximum sum of all these bits, when all of them are 1, is going to be 8 plus 4 plus 2 plus 1, that's 15, which is exactly equivalent to F in our hexadecimal number system. Alright, now let me also cover up one conversion over here, but this video is getting long. I'll probably do that in the next video.